All right, so this particular related rates problem says that the decibel value n of a sound is given by n equals 10 common log of I over 10 to the 12, where I is the sound's intensity measured in watts per square meter. Okay, if the intensity of a sound is increasing at 20 watts per meter squared per second, how fast is the volume of the sound changing in decibels per second when the sound is 70 decibels? Okay, so what do we know? Well, we know the equation. Okay, we know that n is equal to 10 times the common log of I over 10 to the 12. And that's significant because in this case, like off the top of your head, you probably didn't know that. In a lot of the other examples that we've done, I haven't really bothered in a lot of cases to write the equation because for the most part, you knew. You knew what the equation was. I didn't have to specify it. But in this case, you probably didn't know. We know that the intensity is increasing at 20 watts per meter squared per second. Okay, what I want is how fast the volume is changing in decibels per second, and we're given the one instant here where the n value here is going to be 70 decibels. Okay, so let's jump right in and start looking at it. So we know that n is equal to 10 times the log of the intensity over 10 to the 12. Now before I jump in and take the derivative of this, I actually, and I'll zoom in a little bit, when I see something like this with a logarithm in there, I tend to want to get a little bit lazy here, and I'm going to split this thing up. So this will become the common log of I minus the common log of 10 to the 12. So I can take that division and split that up into a subtraction. And then this will become 10 times the log of I minus, now the common log of a power of 10, they are just going to become 12. Okay, that's one of our rules of logarithms here. A common log and a power of 10, those are inverses of each other, so that's going to collapse to that. And so this becomes 10 times the log of I minus 120 when I multiply that 10 through. Okay, so now I'm going to take the derivative of this. So dn by dt, which is thankfully that's what we're looking for here, okay, is going to equal 10. Now the derivative of that log is going to be 1 over I times the natural log of the base here, which is going to be 10. And then I'm going to multiply by di by dt. Okay, good. Now I'm going to start to plug in the stuff that I know. Okay, and in this case here, there's not a whole lot, but I don't know what the intensity is. Isn't that interesting? I know that the intensity is changing at 20 watts per meter squared per second. What I got to do here is I got to figure out what goes right there. So now what I got to do is I got to come back up to my original equation here, and I got to figure out what that intensity is. So I'm going to plug 70 in, and I got to figure out what my intensity is. So this will be the log of I over 10 to the 12. So I'll divide, and I'll get 7 is equal to log of I over 10 to the 12. I'm going to get rid of the logarithm by converting this to the exponential. So this will be 10 to the 7 is equal to I over 10 to the 12. Okay. And now I'll just multiply it up here. Now, because the base here is 10, when I multiply by this, I'm just going to add the exponents. This is going to be 10 to the 19, which that's huge, is my intensity right there. 10 to the 19. Now, I could evaluate that in terms of, like this is now 10 to the 19 watts per meter squared here. And I could probably go through and evaluate that in terms of scientific notation, but I just needed that value to plug into here. That's what I'm going to do. I'm going to plug that into here. This will be 10 to the 19. Okay? And so now, in the numerator here, I'm going to have 200 divided by 10 to the 19. And actually, what I'm going to get here is, actually, we'll do it like this. This is going to end up being, 200, I'll do it like this, over 10 to the 19, natural log of 10. And I'll do a little bit of simplifying, but there's not a whole lot to be done. That'll be like 2 over 10 to the 17 natural log of 10 here. And so that's probably not really clear, but this is going to be our decibels here per second, I believe. That's probably not terribly clear, so let's figure out what this is. This is going to be divided by the natural of 10. This is going to be 8.7 times 10 to the negative 18 decibels per second. Okay, in other words, it's not getting a whole lot louder at that particular moment in time. And actually that makes a lot of sense. The decibel scale is measured on a logarithmic scale. So we're talking about really, really big numbers for intensity. And that's why when I got 10 to the 19, that actually makes a lot of sense here. So when I compare 20, like just 20 watts per meter squared to what like the intensities are at 70 decibels, this is just ridiculously small. So yeah. Turns out that's not much of an increase at all in terms of the volume.